Welcome back, Math 1910. We are starting chapter 4. Alright, so we're going to start out in section 1 here. And we're going to talk about antiderivatives and indefinite integration. Alright, so what does that really mean? Well, when we've been taking the derivative, right, we start with the position function, okay, then we take the velocity, which is the first derivative, then we take the acceleration, which is the second derivative. Now we need to learn how to go the opposite way. All right, we're not going to get super in depth in this section, but as we go through chapter 4, we'll get stronger with our antiderivatives and things like that. But I should be able to, after this chapter, give you an acceleration, and you should be able to work your way all the way to the position function now. So now we're working in the opposite direction when we do this. Okay, so if we take a look at this, our goal is we want to find a function f whose derivative is 3x squared. So we're working the other direction now. So it's very important as you're working through these that we keep an understanding of the difference between what a capital F is and what the lowercase f is. Okay, we used lowercase f's for when we took derivatives and things like that. Now when we use an uppercase F or a capital F to derive our functions, they are going to be the antiderivatives of the original function. Okay, so if we take a look by definition, okay, a function f is the antiderivative of lowercase f on an interval I when capital F prime of x equals f of x. What's that saying is if I take the derivative of the capitalized f of x function, I will get the original f of x function that I started with. Okay, and that's a lot of important information for you guys to be able to check all your answers. Take the derivative of your antiderivative and make sure that you end up with what you started with, sort of thing. All right, and I'll go through those as we do some examples. Okay, so even if we look at the example here, right? If I were to give you the equation 3x squared, all right, and ask you, what's the antiderivative of that function? You're looking for the function that if you took the derivative of that function, you would get 3x squared. Okay, so we're working backwards. So we can clearly see that the antiderivative of 3x squared would just be x cubed, right? And how would we know that? Because if we took the derivative of x cubed, we would get 3x squared. So we're going back and forth between the two. Now, that doesn't mean the answer will just be x cubed. Okay, it could be multiple variations. It could be, x cubed minus 20, x cubed plus 10, x cubed plus 5. We don't really know what the constant was that you took a derivative of. So we get what we call a general solution for that. So we have some sort of constant that we represent with the letter C. Later in this section, we're going to get through what the particular solution is, means that if we had initial conditions, we could actually find what that constant of integration is. Okay, but for our purposes, when we take the antiderivative of an indefinite integral, okay, meaning we don't have limits, and I'll get into what that means in a little bit, but what that means is we always have to write plus c when we take the antiderivative of a function. That gives us the general solution, and then if we are given initial conditions, then we can find the particular solution. All right, so if we look at theorem 4.1 here, it says capital F is an antiderivative of lowercase f on an interval I. Then G, capital G, is an antiderivative of f on the interval I if and only if capital G is of the form g of x equals f of x plus c, all in capitalizations, okay, for all x in I where c is a constant, okay? So we're trying to find, we don't know what that constant was, because, right, if I gave you the equation and said, hey, take the derivative of x squared plus 10, right? You would tell me that it's just 2x plus 0, right? Because the derivative of 10 is 0. However, since we don't know when we're going the other direction, when I tell you an antiderivative, you don't know if that 0 was a plus 10, a plus 2, a minus 5, a minus 15, right? So we're representing that with the letter C. So a lot of your homework problems in here, it's going to be the antiderivative of any of the functions, and the last part will be a plus c. Please don't forget the plus c portion when you're doing that. And remember that plus c, that's the constant of integration. We don't know exactly what that value is, but we know that somewhere along the line, when you took the derivative, you had to have taken the derivative of some sort of constant, all right, because that part had to go to 0. Okay, so we just have to make sure that we work backwards smart. Okay, so remember when we do that and we have the plus c, that's going to be the general solution. So anywhere on your homework and test, when I ask for the general solution of the indefinite integral, you will just give me the antiderivative of whatever's given to you plus c. Okay, so just make sure that we're paying attention to this piece. All right, if we're talking about a differential equation, that's in terms of x and y, that involves derivatives of y. Okay, so if we have to do this, if we have y prime equals 3x and y prime equals x squared plus 1, those are differential equations, okay, because it's in terms of dy or y prime as we do this, okay? So let's do an example here. So we want to find the general solution of the differential equation y prime equals 2. So what you should be asking yourself in your head, okay, is what function can I take the derivative of and get 2? In your head, we're going to do the basic ones here. You should know that that function should be 2x, right? The derivative of 2x is 2. So if we're taking the antiderivative of just a constant value, so it could be 2, 10, 100, 50, negative 10, negative 2, the antiderivative will always be that constant with an x next to it, okay? Then, since we're finding the general solution, it's going to have to add the plus c. And you can always take the derivative of your solution to check yourself. So we have to know, all right, the antiderivative of 2 is going to be 2x. And then since it's an indefinite integral, okay, or an indefinite antiderivative, we have to do that constant of integration. So our final solution should be 2x plus c. And remember, that's our general solution because we don't have any initial conditions to find out what the value of c is. Now, initial conditions, I've mentioned it multiple times, but that's a given solution. So I would tell you, hey, y is 10 when x is 1, or something along those lines. It'll make sense kind of as we move forward. But if I take the derivative of this general solution here, if I take the derivative of 2x plus c, all right, the derivative of 2x is 2, the derivative of c is 0, so I end up just getting y prime is 2. So that's a way you can check yourself. All right, make sure that your general solution, if you take the derivative of your general solution, you should get the derivative of what you started with. Okay, so just make sure that you're checking yourself. Make sure that you don't forget the plus c as we do this. Because remember that plus c can be any possible value right now for the general solution. So that's why, you could graph this a million different ways here because we don't have a defined value for c. So remember that that's the general equation when we do this, okay? So for us, okay, if we have a differential dy dx or y prime, okay, equals f of x, we're going to write it as dy equals f of x dx. That's really kind of, we're working backwards here, and that'll make sense as we start writing up what an integral is, okay? When we do an integral, it's using the integrand sign, okay? The integrand, that's the very last, sign that you see here on the screen. Okay, that little squirrely, really capital, looks like we took an S and then stretched it vertically. Okay, that's called an integrand sign. Okay, so sometimes we're going to have limits of integration. So that defines the interval that we're going to integrate over. Or sometimes there's no limits shown on this integrand sign. It's an indefinite integral. Okay, so indefinite means we don't know what that value of c is, so we're going to write it out for all values of c, or whatever that constant of integration is. All right, so if we write this down, okay, we can see what the integrand is. It's that weird looking symbol, so that's our integrand symbol. F of x, that's the function, okay, of integration, and that's being told to us by dx. If that was dt, we would be doing the antiderivative with respect to time. Since this is dx, we're doing the antiderivative with respect to x. So that'll, affect the function that we're doing in there. So it's very imperative that you understand the variable of integration always goes with whatever that d is. So dx, dt, dv, dA, that would be the variable of integration in each one of those. Now, remember, we've been talking exclusively about the constant of integration, so for the general form, you will always add plus c, and we show that after we've done the integration, we represent it with capital F of x, so we know that it's the antiderivative of the original function. Okay? Now, I've been throwing antiderivative with you and indefinite integral. They mean the same thing. So if I ask you to integrate something, you're taking the antiderivative of it. If I just ask you to take the antiderivative, you're taking the antiderivative. Antiderivative means the same thing as integrating. You know, sometimes we want to represent it with an integrand symbol. Sometimes we just know, hey, I need to take the antiderivative of this. So down there, right, that means the same thing. Okay, so the inverse nature of integration and differentiation can be verified by substituting f capital prime of x for f of x in the indefinite integration here. Okay, so if I integrate f prime of x dx, I get f of x plus c. Okay, that's the inverse of differentiation. Integration is the inverse of differentiation. Okay, the opposite. Remember, then differentiation is the inverse of integration. So if I take the derivative of the integrand, I get f of x. It's like they cancel each other out, if that makes sense. So if I'm taking the derivative of an integral, they cancel each other out, just like a square root and a square sign, right? So if I have the square root of x squared, I know that the square root and the x squared cancel each other out, so I'm just left with x. So right in the first example, right, the integral and the derivative of capital F of x, those cancel each other out, so I'm just left with f of x plus c. In the second example, right, I'm taking the derivative ddx of an integral. The ddx and the integral symbol cancel each other out, and we are left with just f of x. All right, so here's some basic rules. These are written down in the front cover or the appendix of your book. Okay, so if we're differentiating, okay, so on the left, that's everything that we learned in chapter 2. All right, so the derivative ddx of a constant is 0. Okay, the derivative of anything that's a constant times x, so kx, will always be k. Okay, we've done everything on the left-hand side. Okay, now everything that's new to us is on the right-hand side. So if I integrate 0 dx, I'm left with some sort of constant c. Okay, if I integrate k dx, I'm going to be left with kx plus c. So that was an example. If we integrate 2 dx, I would be left with 2x plus c. Okay, next one. If I have, some sort of constant times a function, okay, I can pull that constant out, right? So if I have, if I'm integrating kx, let's say, the k can come in front, and the integrand of x, all right, my antiderivative of x is x squared. So I would be left with kx squared plus c when I did that. And the same rule applies for integration as it does for derivation, or differentiation, sorry. When we have a sum and difference, we can break that integral into 2 separate integrals, all right, of each individual function. Most important one is the power rule. You're going to use that one a lot. So the very bottom one for integration. If you have an integral of x to the n dx, you need to know that it's x to the n plus 1. Okay, so that's the opposite of when we took the derivative, right? On the left-hand side, if we took the derivative, right, the power came down in front and we subtracted 1 from the exponent. Now, what we have to do is add 1 to the exponent, so it'd be x to the n plus 1 divided by that new exponent, n plus 1. Because when you take the derivative, it's going to have to cancel out with something in the denominator. So it's very important that you understand the power rule for integration, all right? And we'll go through some more examples in class. I might have 1 or 2 here on the slides, but It will get stronger with that in class. Okay, write down all the basic integral rules. If you know the derivative, you know the antiderivative. Okay, especially when it comes to trig functions and things like that. So make sure that you have all these written down, okay, on a side note for when you're doing your homework and those sort of things, and just know how to use them. So if we get a function that's secant squared of x and we have to integrate it, you need to know that the integral of secant squared of x is tangent x plus c. Now, it should make sense to you though when you take the derivative of tangent x, it's secant squared. So really, if you know your derivatives, you know your antiderivatives when it comes to these trig functions. All right, so make sure that you pay attention to that. And just like before, the co's, when we took derivative, the co's were all negative. So you can take a look and see here which ones will be negative. All the co's are still negative here with the antiderivatives of their functions. When we end up with a cosine type function, or not a cosine, but a c function, right? A so cosine, cotangent, cosecant. Those are what I'm talking about. Okay, so make sure that you have those down. All right, so let's talk about the antiderivative of 3x. Maybe you could pause the video and give this one a shot and see if you get it right. All right, so we're going to use the power rule here when we do the antiderivative of this function. Okay, so when we do this, okay, we have to do n plus 1 over n plus 1. Okay, if we have 3x here, we know the exponent on x is a 1 right now. Okay, so I'm going to have to take 1 plus 1, so that's going to give me x squared. So I'll have 3x squared divided by 1 plus 1. So I'll end up with 3x squared divided by 2, plus a constant of integration. So I will end up with 3x squared divided by 2 plus c. All right, so we're undoing the power rule there. Okay, so we're going to take the integral of 3x dx, and I'm just walking you through what I just kind of talked you through, visually now. We have 3x squared dx. We pull that constant down in front. So now we're just going to take the integral of x dx. All right, and that exponent on x right now is a 1. All right, so we have to do, 1 plus 1 divided by 1 plus 1 when we do that. So that's where we get the x squared over 2 times 3 plus c. And I'll do more of these in class, all right? So I'll write out, the specifics and fill in the algebra gaps and things like that. But essentially, we're undoing the power rule, okay? So maybe as you're going through the slide, look at your power rule that you wrote down and see how this impacts it. But essentially, it's x to the n plus 1 over n plus 1, all right? So remember, the exponent is 1, so 1 plus 1 is 2, so that's why it's x squared. And whatever that exponent is, so since it's x squared, x to the 2, we're going to divide by that 2. So, that should be pretty simple for you. And then that constant 3 stays in front. All right, and you can check yourself. If you take the derivative of 3x squared divided by 2 plus c, you will get 3x, all right, plus 0. So you can always check yourself on that one. Okay, so be able to go back and forth between the derivative and the antiderivative, or the integrand as we call it. Okay, so how do we do it? All right, original integral, you're going to rewrite it, integrate it, and then simplify it. All right, rewriting it means what? We're going to either pull out that constant function or write it as a sum of two different integrals, or those different things, so that we can get back to our basic rules and apply them. All right, so remember that plus c gives us a bunch of different solutions. Okay, so if we take a look at an original equation here, so if I give you y equals the integral of 3x squared minus 1 dx, you should be able to calculate the antiderivative is going to be x cubed minus x plus c. All right, and like I said, I'm going to do a bunch of these in class. Now that plus c, look at what it can do. It can be any one of those values. There's no way for us to know, so that's why it's a constant of integration. Okay, so what we can do is really, once we have initial conditions, we can use it to satisfy a value. So if you look here on the figure, f of 2 equals 4. Those would be our initial conditions. That means when I go back to my general solution, I would plug in 2 for x and set it equal to 4 and solve for c. Okay, so that helps us find what the value of c is. So then I would have what? 4 is equal to 2 cubed minus 2 plus c. So when I solve all that out, c ends up being negative 2. So I get the function f of x equals x cubed minus x minus 2. Okay, because we used initial conditions to solve for that. Okay, that's finding the particular solution. The only way to find a particular solution is if you have initial conditions. Okay, initial conditions tell you that a curve passes through a specific point. Okay, so in the example we just talked about, the curve passes through the point 2, 4. So that's where I stepped through and I used the figure here on the right hand side. Okay, those are our initial conditions. We applied the initial conditions to the general solutions, right? F of 2 equals 4. So you substitute in 2 for x, set it equal to 4, solve for the value of c. Okay, so f of 2, so I just walked you through that. We're walking through it now again visually. So, right, 2 cubed is 8 minus 2 plus c because it was just minus x, right? So it was x cubed minus x plus c. So it's 2 cubed minus 2 plus c is equal to 4. We solve for c, c is negative 2. So we obtain what we call the particular solution. We use the initial conditions, we took the antiderivative, we substitute in the initial conditions to get the value of c, all right, and then we put c back into our antiderivative. So our solution, our particular solution, is x cubed minus x minus 2. So if you take the derivative of x cubed minus x minus 2, you end up with 3x squared minus 1, all right, which is our original function. Sorry, going through slides here, right? We integrated 3x squared minus 1. So you can check yourself, oh, I did get the right thing, okay? So be able to go back and forth between the general solution, the particular solution, and the derivative of the function to check yourself. All right, so let's take a look here at one more example. All right, we want to find the particular solution. So first we need to find the general solution, and then we want to find the particular solution that satisfies the initial conditions f of 1 equals 0, which means we're going to substitute 1 in for x and set it equal to 0 once we take the antiderivative of the original function. Okay, so we're going to integrate 1 over x squared. Best way for us to do that is to rewrite 1 over x squared as x to the minus 2 and then integrate it. So we're going to set this up, all right, the integral of 1 over x squared dx, and then when we rewrite that, well, I almost didn't get that out. We're rewriting the integral as x to the minus 2 dx so that we can use the power rule, okay, for integration to undo that. X to the n plus 1 over n plus 1. N in this case is negative 2, so we have to do negative 2 plus 1 divided by negative 2 plus 1. So it's going to be x to the minus 1 over minus 1. Okay, when we do that. So we're going to get x to the negative 1 over negative 1 plus our constant of integration. Now, since we have our initial conditions, right, we have f of 1 equals 0. So I'm going to replace the x with 1 and set it equal to 0 and solve for c. Okay, so when we do that, we simplify it down, right? We have negative 1 over x plus 0. We're going to set that equal to 0 and solve for x. In this case, when we do that, c yields a 1 for us. Okay, so our general equation is negative 1 over x plus c. Our particular solution, okay, is going to be negative 1 over x plus 1. That's our particular solution, and we used the initial conditions to get that particular solution. All right, so let's recap. There's two forms here, right? We have a general solution, which means we just take the antiderivative of a function and we do plus c, some sort of constant of integration. Or we have what we call a particular solution. So we find the general solution first, all right, some sort of antiderivative plus c, and then we use the initial conditions to solve for what the value of c is, all right, and then we have our particular solution, okay? Now I'll go through a few more examples in class so that we can really hone us in on doing antiderivatives and things like that. So make sure you're following like the streaming one if you want to on this one, if I'm doing a streaming one at that time. All right, else email me with any questions or anything like that. But this one's just building our foundation for antiderivatives. Okay, so remember antiderivatives, we're working backwards from everything that we did in chapter 2, all right, and 3 in essence, but we learned it all in chapter 2. Okay, all right guys, as usual, email me if you have any questions. Else, see you in class. Have a great day.